Hello everyone. As I explained to you in the email that I sent you, for the next few weeks, until otherwise instructed, we're going to have online lectures. So I'm going to start discussing the material from chapter 18. Hopefully we can basically continue with the schedule that we have in regards to taking the quizzes, and we were already geared up to do some online material, so this hopefully shouldn't be too much of a difference, or too much. Hopefully it's not going to have too much of an impact on your learning. But if you feel you need more help, please don't hesitate to approach me. I'm going to have online office hours, and I'm going to send you Zoom invite links so that you can actually get online and have a face-to-face with me and talk to me and ask me questions, most likely during the same time that used to be my office hours. You can do that. And other than that, if you need anything, just send me an email, and hopefully we can find a way to address your concern. Discussion today is about two-port circuits, and as I explained to you, it's from chapter 18 in the book. There will be a quiz this coming Thursday, from the material. The material is really simple, and I'm going to do as many examples as I can so that you're prepared. But please do approach me if you have questions about the homework, and hopefully we can prepare you for the time that you have to take the quiz. Okay, so as you can see here, this is basically a two-port circuit, and what's different than what we normally used to do in a circuit is that, if you recall, by now we are kind of used to putting boxes around circuits or parts of the circuit that we are analyzing, and model them using the voltage current behavior that we see from the terminals that is connected to that box. The most useful or the most common that we have done was called the Thevenin or Norton modeling, where we basically said we can put this box around any circuit and then model that with a source and a resistor. Depending on whether or not we do Thevenin and Norton, the source and the resistor would be connected differently. Now, what is different in this new discussion that we're going to have is that in certain cases, and we have already seen some of that in this course, the circuit or the box that we put around the system is going to have more than one port, or more than two leads or terminals connected to it. And generally the reason that we consider doing a modeling like that, is that we would differentiate an input that is connected to that circuit from an output that would be connected to a different part of the circuit or a different part of a system. You don't have to have that case. This doesn't have to be called input and that other one output for this to be useful, but a lot of times this is actually how a two-port system is going to be used. With that in mind, there's these certain kinds of two-port circuits that we are going to discuss mostly in this chapter, and that's when there are certain limitation or conditions that we consider for the circuit. For example, we are going to assume that there is no independent source inside that box, and also we're going to assume that the current that is going into this port on the left, which we are going to call it port 1, is basically the current that is going into that port is the same current that is coming out of the port. So we're not going to label two different currents for these two terminals connected to that port. And the same is true for port 2. And what that means is that I1 is going to the port 1, and the same I1 is coming out of that port, and I2 is going to port 2, and I2 is coming out of that port. And obviously this is a specific situation case for KCL that you could write for this node, where all the currents going in has to be equal to the current out. So generally speaking, this doesn't have to be the case, but for the circuits that we're going to discuss, this condition is actually met. That said, what we are trying, the goal of the analysis is to find out how the voltage and currents of these two ports relate to each other, and find an equation that basically simply can tell us how to go from one set of these parameters to the other set. Now let's discuss what we mean by set of parameters. So we have the current going into the port, we have the voltage of that port, I1 and V1. Then we have current that is going into port 2, and then the voltage of port 2. So we have a set of currents, I1 and I2, and set of voltages V1 and V2 associated with port 1 and port 2. Now, what we are trying to achieve is to say, can I find, say, any two out of these four parameters when I know the other two? So that's the goal. Let's say, for a simple situation, I1 and V1 is given, and I'm looking for a way to, without really knowing what the circuit is, to calculate I2 and V2 just using equations that model the behavior of that circuit. So down here you see actually an example of a two-port model, and which one of the two parameters you're going to choose to write as a function of the other two is basically could be any of them. So you can choose I1 and V1 as your known variables, and then I2 and V2 as your unknown that could be written as a function of I1, V1, but you can choose I1, I2 as the known variables and try to find V1 and V2 as a function of the other two. So it's basically a choice of 2 out of 4. And that gives you 6 different ways of writing, basically arranging these equations. Now, the assumption is that these circuits are linear. This course is called linear circuit analysis. And therefore the relationship between the sets that you choose as a function of the other set is going to end up being a linear equation. Okay, so you can write V1 and V2 as a function of I1 and I2. You can write I1 and I2 as a function of V1 and V2. You can write V1 and I1 as a function of V2 and I2. You can write V2 and I2 as a function of V1 and I1. And finally, you can write V1 and I2 as a function of I1 and V2, or V2 and I1 as a function of V1 and I2. Now, depending on which one of these 6 you choose to do, and it's really a matter of what's the most convenient for the kind of analysis that you're doing. For example, I give you an example. If you're dealing with a situation where this is your input port and you know what the voltage and current of the input port is, because you're actually applying those 2 values to the circuit, then finding V2 and I2 as a function of V1 and I1 would have been prudent, and it would be useful. Now, I would tell you that depending on which one of these you choose, the factors or the equation that you write is going to have a certain format, and based on that format there are certain names that are used, terminology that is used to discuss the relationship. And some of these relationships are more commonly used than the others. So the 2 first ones that are written here, V1 and V2 as a function of I1 and I2, and I1 and I2 as a function of V1 and V2, are actually the most common ones used. Like I said, because we are dealing with linear circuits, this function would be a linear function. So let's actually take this first one and expand it. So we're going to write V1 as a function of I1 and I2, and it's a linear circuit, so it would be a linear function of I1 and I2, and there's no independent source inside, so it would be in this specific form that I'm writing. It's going to be called Z11 I1 plus Z12 I2, and I'll tell you why we call these Z11 and Z12 later on. And then V2, it would be Z21 I1 plus Z22 I2. So this is the most general way of writing V1 as a linear function of I1 and I2. Is basically a factor multiplied by I1 plus another factor, constant factor multiplied by I2, and the same for V2. Now, as you can see, we have written them in a certain way and given them a specific kind of term that is meaningful. So first of all, why are we calling them Z11, Z12, Z21, and Z22? Because you can simply write this equation, the same 2 equations, in the form of a matrix. So if I take V1 and V2 and write it in a vector format, then I take all these Z values and put them in a 2 by 2 matrix. So that would be Z11, and this would be Z12, and this would be Z21, finally Z22, and you take that and multiply that by I1 and I2, and you obviously get the same set of equations. Now, this matrix right here, it's called the impedance matrix for this 2-port circuit, and hence calling it Z, basically. That's why this is called Z. Now, why would it make sense to call this an impedance matrix? First of all, we're writing all these equations, as you can tell from this picture, we're writing it in the S domain. And in the S domain, as you can see, something a number is getting multiplied by a current and it gives you a voltage. Therefore, the unit for that is the unit for this number right here would be basically a voltage divided by a current, which is O. And that's the unit of impedance in the S domain, or the unit of an impedance, actually resistance in the time domain. They're both the same, as you know. And therefore it completely makes sense to call these impedances, and because they have the unit of ohm, and they get multiplied by these two currents and it gives you these voltages. And this is one of the most common ways of representing a two-port circuit. So before we move on and talk about other ways of actually rewriting the same equations, let's practice writing this equation set in this form, and in other words, finding the Z parameters or the impedance matrix for this specific circuit that is down here. So now, how do we do that? It's always the same way. You go back to circuit analysis, and when we, from this point on, we go back to the three-step algorithm that we always used. So let's do it. In other words, for any circuit, there is nothing else that you need to do, and I have repeated this so often that I think by now you're bored. So we label the circuit. So that would be one node. This is one node, and this is another node. I'm gonna take that as my ground, and when I do that, this automatically becomes V1, that becomes V2. Now there's a current here. Let me actually, I don't want to repeat writing I1, so let me redo the labeling. What we did was all right, but it's easier if we do it this way. So this is my ground, this would be my V1, this would be V2. I1 is going in, so I'm going to actually use the same I1 right there, and I2 is going in here. Now I'm going to assume I3, I4, and I5 for the other three components here. Now, as you can see, it's slightly different than what we did, because it appears that we are actually labeling current for a piece of wire. This is really not the case. This port is assumed to be connected to a different component, and the same with a port right there, and therefore this current is actually the current of that component that is the two-port circuit is connected to, and we need to take that into account because we are making the assumption that these are actually connected, even though that it looks like it's not connected. To develop these relationships, we consider these to be connected for the most general case, and then once we develop that most general case, you can always go back and assume that one or any of these is equal to 0. For example, you can assume that, okay, this port is not connected to something, at which point immediately I2 is going to go to 0. But at the time of developing the equations, we're not going to make that assumption. Write all the equations for the most general case, and then go back and make a special assumptions if need be. Okay, so now let's move on and start writing the equation for this circuit. So we have 2 nodes to write KCL for. So I'm going to write from here. So KCL. There are 2 KCLs. For V1, the node V1, I1 is going in, and then I3 and I4 are leaving that node. For the node V2, I2 is going in, and I4 also is going in, and I5 is leaving that node. Now, as for the equations for components, we only have 3 resistors, so we're going to have to write 3 equations for those 3 resistors. So I3 is equal to V1 minus 0 divided by 20. I4 would be equal to V1 minus V2 divided by 5, and I5 is equal to V2 minus 0 divided by 15. Okay, so this is it. This set of equations describes the functionality of this circuit. There is no other thing that you need to know about this circuit. Now, what we wanted to do initially is to find V1 and V2 as a function of I1 and I2, and that's what's left to do. We just have to take these 5 sets of equations and manipulate them so that they're only the only parameters that are left are V1, V2, I1, and I2, and arrange them so that we find V1 and V2 as a function of I1 and I2. Okay, so now we take these 2 KCL equations and replace I3, I4, and I5 as a function of V1 and V2, since our target is to actually get rid of I3 and I4 and I5 and find equations that are only function of I1 and I2. So I1, I2, and V1 and V2. So I1 is equal to V1 divided by 20 plus V1 minus V2 divided by 5, and I2 plus I4, which is V1 minus V2 divided by 5, is equal to V2 divided by 15. Now we can take these 2 and start manipulating them to bring them into the final shape that we're looking for. So I'm going to multiply both sides by 20, and so we have 20 I1 is equal to 5 V1 minus 4 V2, and down here multiply both sides by 15, so 15 I2 is equal to 4V2 minus 3V1. So now I'm going to manipulate these two equations and find V1 and V2 as a function of I1 and I2. One way to do that is to just add these two sides up, and that way I get rid of V2. So 20 I1 plus 15 I2 is equal to 2V1, which immediately gives me an equation that is V1 as a function of I1 and I2, and that's V1 equal to 10 I1 plus 7.5 I2. Now I can use this, put it into this equation, and write V2 as a function of I1 and I2. So now I'm using this equation. That would be 15 I2 is equal to 4 V2 minus 3 times this, 30 I1 minus 22.5 I2. And we can manipulate this, and based on that, write V2 is equal to 7.5 I1 plus 9.375 I2. So now these two equations, this and this, is what we were looking for. Again, if you have a calculator where you can actually put in these equations, then you can ask the calculator to basically choose 2 out of these 4 parameters as your knowns and find them as a function of the other 2, and you don't have to do any math, but if you do want to do math, this is how you do it. So based on this, if I want to write these 2 equations in this form and figure out what the z parameters are, it would be V1 and V2 is equal to the matrix of 10, 7.5, 7.5, 9.375 multiplied by I1 and I2. So in other words, Z11 is 10, so Z11 is 10 ohm, Z12 is 7.5 ohm, Z21 is also 7.5 ohm, and finally Z22 is Z22 is equal to 9.375 ohm. So now let's make sure that we haven't forgotten about why we're doing any of this. Once I have these 4 values, now I no longer need to tell a user of this circuit how this circuit is designed, what components are inside, or anything like this. All I need to do is to give them this matrix or these 4 parameters, and based on that, the user can actually replicate the functionality of that circuit using this equation that we have right here. In other words, there is now an equation given these 4 values that we just calculated down here. There is a set of equation that relates the current and voltages of the 2 ports of this circuit, and they can use it to do any calculation that they need. And the beauty of it is that once you have this set of equation, you can actually derive any other of these 5 other equations that you want. So like I said, it's just a matter of manipulating these equations. Now, the same set of equations, I can actually write them as a function, write I1 and I2 as a function of the voltages, which is exactly what we have here. I don't have to really do anything for that. And then I have this definition. And at that point, the matrix is called something else. As you may imagine, at that point, the matrix actually called the, so this was called the impedance matrix. If you write this, then the matrix, if you write it in this form, then the matrix is called the admittance matrix. And then you're going to have y11, y12, y21, and y22 for an obvious reason, because at that point, your voltage gets multiplied by one of these values, and it gives you a current, which means that the unit for those values is 1 over O, or mu, and therefore you're looking at the admittance of the circuit. We're going to talk about this in more details when we continue the discussion in the next lecture. I'm intentionally keeping the lectures relatively short so that it's less boring. Thank you very much. I'll talk to you later.